Hello. Um, After a long while, I'm back, and today we are going to start with the topic that we were doing in the last class. I think we were doing method of images, and probably we were doing a question, and which was left undone. So I'll start from there, and as I go along, we'll see many other things. Okay. So the problem that I was discussing was in the previous lecture, that is a method of images part 2. You can see it on YouTube also. Uh, this was what we were doing. Okay, this was what we were doing. So I'm going to start from there only. So we were doing method of images. Let me just share the screen. Okay, let me just share the screen. Okay, so we were doing method of images. And these method of images we were doing, I mean, what I was trying to do was, uh, I, I actually I was doing a problem where I was saying that there is a infinite grounded conducting plane. So this was an infinite grounded conducting plane. And we kept an infinitely long line of charge, which is extending towards infinity. And one nearer end is at distance L. And we wanted to find the induced charge density. We wanted to find the induced charge density as a function of distance from O. So we actually found initially what was the induced charge density, induced surface charge density at O, and now we wanted to find what is the induced charge density as a function of distance from O. Okay, so let us take that distance as R. Okay, so let us take that distance as R. And one of the things that I already taught you, that if this is your infinite line of charge, which is grounded, so what I can do, I know that this potential would be zero. So in order to maintain the boundary conditions intact, so in order to make the boundary condition intact, this is what we can do. We can replace this ground, like we can remove this grounded condition, and we can replace on the left hand side an infinite line of charge with a negative linear charge density. So this is what we can do. So you have this length L here. So another at a distance L only. So I will do something like this. So I will place an image line of charge here. It is also extending towards infinity only. So we'll place image line of charge with the charge density minus lambda. The charge density minus of lambda. Okay, and here, and we wanted to find what is the induced charge density as a function of distance from O. So let us take this distance as R. So at a distance x, let us take a small differential element dx. Now, because of this dx, there would be some electric field at this point. So what would be electric field? We know that electric field would be equals to what? So this is your x, this is your r, this distance is r square plus x square raised to power 1 by 2. Okay, so if this is the case, so this will, if I place a unit charge here, so it will push it here. And by symmetry, if I take at a similarly placed differential element, I can say that my net electric field at this particular point would be in this direction, like this horizontal direction that I'm drawing. Okay, so your electric field net would be in this direction. And if this is theta, so I'll write that this is, let's say, E1, because of the one I'm writing, and I'm writing this as 2. So electric field due to this negative line of charge, you can see that direction would be in this direction. This is your E2, this is your E1, and your E net would be equals to what? Your E net would be equals to E1 vector plus E2 vector, and obviously it will be in this direction. Okay. Uh, uh, so, and what would be dq here? So dq would be nothing but it would be equals to lambda times dx. Okay, so what is the net electric field at point P? Let's say this is point P. So net electric field at point P would be equals to 2 times K dq uh, divided by K dq upon this distance, right? So this distance would be simply root over r square plus x square. And if this is theta, this will also be theta. So net electric field in this direction would be uh, uh, E1 plus E2 cos theta. So this will be K dq root over r square plus x square. And there would be this distance. What should I say? Cos theta is x upon root, again r square plus x square. Is that clear? So your net electric field in this direction at this point P, because of these two differential elements, would be this. And why I've taken 2? Because I know that this at symmetrically placed, if I take instead of dx, if I find a symmetrically placed differential element here, so I can clearly see that it is going to add up in this direction. So I've written 2 times in order to justify the same. Is that clear? So your net electric field in this direction, so I'll write it dE. So your E would be equals to what? It will be equals to K. I'll write here. So this would be K integral. What is dq? dq would be, I think, lambda dx, right? So I'll place lambda outside, and this would be 2x, and this is dx divided by x square plus small r square raised to power 3 by 2. And from where to where? So this x would vary from L to infinity. So it will incorporate the contribution from like this from all infinitesimal small differential element on this line of charge. And equally in magnitude, such contributions I will account from this particular image line of charge. So in totality, I'll find that net electric field at point P would be in this direction, and therefore I have written 2 times. Bharat, is that clear?
Yes, sir. So this charge density can be of finite length also, no?
This charge density can be a finite. But right now, because the question that I was discussing in the previous class, we did the question for finding the induced charge density at point O. Now the same question I'm doing as a function of distance from O. And this was infinite line of charge in the previous question that I was doing. So therefore, I'm continuing with that question. So you
Okay,
can
sir.
have this uh, if you want to have a question where you can have an finite length of charges. But the question that we were discussing was an infinite line of charge. Is that clear?
Yes, sir.
Okay. And two, because if this is the dq, and if you want to find electric field to this dq, because of the image line of charge, another symmetrically placed dq uh, would also contribute in such a way that the net electric field would be in this direction. It will be 2e cos theta. Is that clear? So that's why I've taken 2 here. Is that clear? So now this is k lambda, and now if I integrate it, I'll get, uh, I hope it is like minus 2 upon root over x square plus L square. So I'll forget this, forget about this negative, I'll do this. And eventually I can find that net electric field at point P would be k lambda, 2k lambda divided by root over L, L square plus R square. And I've already told you that near the, however, we'll derive it someday, how near a conductor, the net electric field in the perpendicular direction is equals to sigma upon epsilon naught. And this sigma would dictate your induced surface charge density at this particular point. So induced surface charge density given by sigma upon epsilon naught can be written as lambda upon 2 pi epsilon naught root over L square plus. So eventually your sigma as a function of r, you can write it as lambda upon 2 pi root over L square plus r. Is that clear? So this will be your, and if you remember at O, the induced surface charge density was coming out as lambda upon 2 pi L. And that is very clear. You can see that if I place r equal to 0, you will be at 0.2. So this was the question that I was doing in the previous lecture. Okay. Now let us see the case of a conducting ring of charge q placed at a distance L from the infinite grounded conducting. So if you have an infinite grounded conducting plane, and if you had this ring having charge q here of, let's say, radius capital R. And here I will not be discussing another cases because I have not yet derived the potential apart from axis. So that will again contain Legendre's polynomial. It is a very different thing to calculate. So we'll only find what is the induced charge density at point O, which lies on the axis of the ring. So apart from the axis of the ring, then it will become a very difficult problem because we have not derived the potential for the ring apart from the axis point. Look, generally what you see whenever you are told find the potential to the ring, so what you do, you find that potential only on the axis. And there comes an ambiguity, and usually people ask that there's a very standard question of standard 12th also, that if you have charge, let's say q here, and if I place a minus q here, so what will happen? It will attract this charge, so it will go this way. And because of the momentum it carries, it will obviously cross this ring, and again it will start getting attracted, so it will execute simple harmonic motion. I'm just diverting a little bit of attention to a different other problem that I'm going to address in later on. But this is a problem that you know that if you have this charge q, and if I place a minus q here, so obviously this minus q is going to start execute. This minus q is going to execute a simple harmonic motion if that like distance is very small as compared to the radius of the ring. I mean, if you remember that problem. Bharat, do you remember
Yes,
that?
sir.
Yeah. So now
Yes.
usually students ask one of the question that when we were doing this when we were doing the Laplace's equation, and if you consider the boundary of the system in this way, that it contains both charge q and minus q, so obviously the total charge is zero. So you can obviously apply del square v equal to zero in this entire scenario, right? And one is tempted to ask that probably whenever I've taught you this Laplace's equation, one of the applications is Earnshaw's theorem, and which suggests that no equilibrium point in electrostatics can be a stable equilibrium point. Rather, all the points are unstable equilibrium points. And one is tempted to ask that if this is the case, whatever I'm saying is the case. For example, when we discussed this, I think if you are aware that we discussed Earnshaw's theorem, uh, one is tempted to ask that how is that the case? Then it starts oscillating. How would you justify oscillations and Earnshaw's theorem in one line? Because see, Earnshaw's theorem says that if you have this del square v equal to zero, then we cannot tolerate any minima. And since we cannot tolerate any minima, so you cannot have any stable equilibrium point. And if there is no such stable equilibrium point in electrostatics, how come oscillations are going to get executed? Because after all, oscillations are executed only at the points of stable equilibrium. Am I positioning the problem right? मतलब तुम्हें समझ में आ रहा what I'm trying to
Yes, sir.
suggest? Okay, so I'm just
Yes.
diverting a little bit from whatever I was teaching. So one of the things that one needs to remember is that the Earnshaw's theorem is a three-dimensional case. So if I'm going to derive this expression for the potential due to ring at any general point, you will be seeing that it again goes into Legendre's polynomial. So only on the axis it may execute oscillation. So on axis there is a stable equilibrium. So that problem is not wrong. मतलब जो problem हम बचपन से करते हैं from NCERT or from wherever sources you have. So you do that problem ना जहाँ पे axis पे oscillations दिखाए जाते हैं. So we'll do those problems also. So one has to understand that Earnshaw's theorem is for three-dimensional case. It is not for a single dimension. Point number one. Point number two. Also, you can find that at any general point it will not be a stable equilibrium point. Only along the axis it will have a stable equilibrium. So here ऐसा नहीं है कि Earnshaw's theorem has become invalid. It is just that Earnshaw's theorem is a valid case only for three dimensions. Because whenever you apply this del square v equal to 0, it is implied that you are doing it for three dimensions. So this is something that I'm going to come at a later state, but I'm leaving it for you to think upon. What I'm trying to make my, like, have I made my ground clear? मतलब question समझ में आ गया ना? मतलब doubt समझ में आया बच्चों का? Usually people ask that if you're doing this, then how come you are going to justify that Earnshaw's theorem? And Earnshaw's theorem is not wrong as such. You can understand that it is completely mathematical, so it cannot be wrong. Like it cannot be wrong as in मतलब वो चीज del square v equal to 0 and v cannot tolerate any minima is a standard concept in partial differential equations. So I don't it cannot be wrong anyway. So one needs to realize what is the relevant physics to defend it. So relevant physics to defend is that Earnshaw's theorem is only valid for three-dimensional systems or three-dimensional cases. So you cannot apply this Earnshaw's theorem along an axis, and you cannot make an assertion that here you see that there's a stable equilibrium. No, you just move at any general point. And for any general point, whenever I'm going to derive this potential, you will be able to understand that this is not as easy as it seems. So right now it's easy. So let us do that. So if at a distance x, I'm supposed to find if I'm supposed to find electric field. So if you're aware that electric field should be equals to kqx upon x square plus r square raised to power 3 by 2. I mean, you're aware of this result, or should I derive it?
Yes, sir.
This is something
सर
that we
सर जो रिंग का केस आपने बताया कि ये थ्री डायमेंशन में वैलिड रहेगा, बट ये वाला थ्री डायमेंशनल केस में नहीं आएगा सर, ये पूरा सिस्टम, बिकॉज एक रिंग
यस आई
एक टू
अंडरस्टैंड जो तुम
डायमेंशन।
हाँ हाँ मैं कह रहा हूँ, लेकिन जो मैं समझाने की कोशिश कर रहा हूँ कि जब भी कभी एक लाइन के लॉन्ग मोशन होगा वहां अनशॉस थ्योरम विल नॉट प्ले एनी रोल। समझ रहे हो? मतलब यहाँ पे एक लीनियर मोशन चल रहा है, so you cannot assert your Earnshaw's theorem here. So I'll come to that point later on, but I'm just putting this thing in your mind that whenever I'm going to discuss, let me know this. मतलब ये चीज मुझे याद दिलाते हैं. So I'll write those things in a better way. अभी एकदम से मुझे याद है, so क्योंकि ये जनरली
ओके
इंटरव्यूज में भी हो सकता है पूछा जा सके तुमसे कि यार और तुम तो यहाँ माइनस क्यों कर रहे हो, एंड देन यू आर डूइंग लैपलास इक्वेशन, फिर तुमसे कोई कहता है कि नहीं ये तो Earnshaw's theorem आप इनवैलिड कैसे कह सकते हो? Earnshaw's theorem is not invalid, but it's completely true. Okay, so we'll come to those things later on. But अभी के लिए समझो, this is something that you know from your standard 12th. If you don't know, I should have मतलब करना चाहिए क्या मुझे? I think मतलब कर सकते हो ना
यस सर,
यहाँ
ये
से
आता है।
कर लिया. This is quite easy. Okay, so electric field is this, and I think potential is given by kq upon root over x square plus r square. So I think these two results I think you are aware of. So this is the electric field and potential at a point O, which is on the axis of the ring. So this is at point O on the axis of the ring. Axis of the ring of charge q, radius capital R. Okay, is that clear? So I hope this is clear. And
यस
what one can do is, let us say this is your so instead of this I'm going to make another image ring. So this will contain charge q, this will, and I'm interested to find what is the first thing that I want to find is what is the induced surface charge density at exact O, because this is what I know right now. This is what I know, because once I'm going to derive the potential uh, uh, due to at any general point, then we'll be able to understand other things. But right now, the results that I know, uh, from that I can find induced charge density at point O. So I want to find induced surface charge density at point O, and what that would be. So I know that my electric field at this particular point, because of this charge q and because of this minus charge q, I can write it clearly that, so let's say this is your 1, let's say this is your 2. So electric field at point O would be equals to electric field due to 1 plus electric field due to 2. Okay, so electric field at O would be equals to what? It will be equals to k q, and let's say this distance is L. So I'll keep this distance as L. So let us say that this is at a distance L. Okay, and we want to find what is the induced surface charge density at point 2. So this will be equals to kq upon kql upon L square plus R square raised to power 3 by 2 plus. Okay. So electric field at point O and I should write it as QL divided by 2 pi epsilon L square plus R square के पास 3 by 2. Is that clear? भरत समझ में आ रहा है अभी तक? And what would
जी
be
सर
induced charge surface charge density? And we know that at a normal to the plane at point O, the electric field just near is given by sigma upon epsilon naught, and where sigma is the induced surface charge density. Here it refers to the induced surface charge density. This is equals to QL divided by 2 QL divided by 2 epsilon naught root over, sorry, not root over, L square plus R square raised to power 3 by 2. And so clearly I can find that my sigma would be equals to Q times L divided by 2 times pi, and you have this L square plus R square raised to power 3 by 2. Okay, is that clear?
यस सर सिग्मा में एप्सिलॉन नॉट कैसे आपने रखा सर ई को
Okay, so just near the conductor, normal to the surface of the conductor, the electric field is given by sigma upon epsilon. So ये मतलब result है, मतलब conductor के just pass
हाँ
पे
जी सर
you have nearby, you can find this. We'll do all those things because I have left the basics for the electrostatics because I thought these are from standard tool, but I'll do it anyway. So method of images एक बार हो जाए, then we'll randomly do certain important topics from electrostatics. However, I will depend more on you. That is, if you're able to do much of the 12th class things, then I'll be doing some advanced things there also. Okay. So one of the cases that I want to,
एक्चुअली
yeah, बोलो.
सर आई एम अवेयर ऑफ दिस बट ये जैसे हम कुछ परपेंडिकुलर कंपोनेंट निकालते थे कोई हम सरफेस क्रॉस कर रहे हैं तो वो सिग्मा एप्सिलॉन नॉट से वेरी करता है ये रिजल्ट वहां से आ रहा है क्या सर
हाँ हाँ एग्जैक्टली मतलब जो कोई भी एक इनफाइनाइट लाइन ऑफ शीट होता है ना, या इन जनरल कोई भी आर्बिट्री कंडक्टर ले लो, है ना, कोई भी आर्बिट्री कंडक्टर ले लो, उसके अंदर यहाँ पिल बॉक्स बना लो छोटा सा, एंड नॉर्मल टू दिस पिल बॉक्स यूल फाइंड दैट इसके अंदर, बिकॉज कंडक्टर है तो अंदर तो कोई भी इलेक्ट्रिक फील्ड नहीं होगा, इनसाइड इलेक्ट्रिक फील्ड वुड बी जीरो, आउटसाइड इलेक्ट्रिक फील्ड विल बी इक्वल्स टू व्हाट, लेट्स से दिस क्रॉस सेक्शन इज ए, and let's say on this surface you had the surface charge density sigma, so your u e outside minus e inside, so your total electric field will be outside, and this will be sigma into a divided by epsilon naught. If you want to find
यस
a
सर
flux, e into a, so this is how you derive the like
तो
for
सर
any
यहाँ पे हमारा कंडक्टर कौन सा है सर जहाँ पे हम इलेक्ट्रिक फील्ड सिग्मा बाय एप्सिलॉन नॉट ले रहे हैं परपेंडिकुलर
here conducting plane, this is your conducting plane. So this was your infinite conducting plane, if you remember, and it was grounded. So we replaced this problem by these two problems. Now this is your conductor. Just nearby the conductor, the electric field has to be equal to sigma upon epsilon naught. This is the fundamental property of conductors. But also we found that at point O, the electric field can be given by this. Sorry. So electric field can be given by the net sum of the electric field due to the ring of charge and due to the image ring of charge. So
सर
this is
सिग्मा इस
also,
पे चार्ज डेंसिटी हमने प्रोवाइड की हुई है क्या इनफाइनाइट प्लेन पे
देखो देखो वापस, let us come to the initial problem. If you remember when we were doing this thing, like याद करो ये वाला problem था. We had this एक plane था and we placed a charge q here. So I told you that because of this
यस
charge
सर
q, there would be some induced surface charge density. And obviously this is
यस
very
सर
difficult to find, है ना, याद करो. So एक strategy क्या थी हमारी कि हम इसको भूल जाएंगे इस problem का, and we'll place minus q here. And we'll try to find electric field at this point. And once you find electric field at this point, then I know from standard 12th class that my electric field, the normal component just outside is given by sigma upon epsilon. And from here I will be able to derive the induced surface charge density. तो अभी हम जो कर रहे हैं या हम जो previous दो lecture में किए हमने mostly we found induced surface charge density, if you remember. Okay?
Yes, sir.
Okay. So I hope this is clear.
Okay.
Okay. So let
Yes,
us try to find what is electric field at this point O. Okay, not point O. Let's say P. Okay, so I'll write here. Let us try to find
and sir, electric field at point O will be in negative x direction.
Yeah, that would be negative x direction, right? Well, direction wise because of this and this. So at point P, because of this ring, you do not have electric field, right? Because even if you find it, or otherwise also because of you don't consider self fields, or otherwise you know this is kqx upon x square plus r square की power 3 by 2, you place x equal to 0. So whatever electric field will be, it will be due to this, isn't it? Whatever electric field would be there on point P, it is due to this imaginary line of charge. Imaginary line of charge, sorry, image ring only. Is that clear?
Yes, sir.
And what it would be in that case? So it would be simply equivalent writing kq, whatever the distance is. This will become 2L now.
2L. Yes, sir.
Electric field at point P would be equals to, so electric field at point P, if I want to write direction wise, it will be equals to minus of k q 2L divided by, I think this would be x 2L ka whole square plus r square ki whole power 3. Is that clear?
Yes, sir.
Okay. And if I say that what would be the potential at point P, what will be potential at point P, then how to find that? How should I find that? So what would be potential at point P? So I'll make this again so that यहाँ पर बना. तो ये रहा हमारा चीज थी. So this was your point P. This was your charge point. This is point P. Now potential due to this would be there because if you remember the potential is potential at any as a function of x on the axis is given by kq upon root over x square plus r square, where r is the radius of the ring and this x is the distance on the axis of the ring. So if I want to find what is the potential at point P, this would be equal to simply kq upon, I think this would be simply r because x is 0 here, and because of this there would be minus kq divided by root over 4l square plus r square because this distance in totality is. So potential at point P would be equals to, if I take common kq upon capital R, it will be equals to 1 minus 1 upon root over 1 plus 2L upon R का. Is that clear?
Yes, sir.
ठीक है, तो इस तरह के questions usually people may ask. Okay, is that clear? Okay. So now let us consider another case which can be a dipole, a point dipole. Let us consider the case of a point dipole of dipole moment p vector. And whenever I'm saying point dipole, it means the distance between the two charges is infinitesimally small. So you can take that distance as small differential dr. Okay? And always remember, whenever it is said that I'm referring to distance, in case of dipoles, I refer the distance from the middle point of the mid of the this separation. Is that clear? मतलब whenever जब भी मैं कभी बात करूंगा कि if I say that my dipole is placed at a distance r, I mean that the midpoint of the dipole is placed at a distance r.
Okay, sir.
Is that clear? So a point dipole of dipole moment p vector. You can take it as a question. Also, you can take it as another case that we're discussing. A point dipole of dipole moment p vector is located at a distance L. Is located at a distance L. Okay, from an infinite grounded conducting, from an infinite grounded conducting plane. And we want to find the force. We want to find the force acting on the dipole, provided this dipole moment p vector is perpendicular to the plane. ठीक है, so हम एक काम करते हैं. Let's say this is your infinite grounded conducting. So this is my infinite grounded conducting plane. And a dipole, let's say I'll write it as A and write it as B, and I'm writing it as point dipole. I'm showing it very exaggerated right now. Okay. So let's say in this direction, my dipole moment is there. And I want to find what will happen because of this image, like this infinite grounded conducting plane. There would be an image dipole created here. And because of that image dipole, it will experience certain force. Is that clear?
Yes, sir.
Okay. So in order to explain this, what I'll do, well, easy करने के लिए, what I'll do, instead of writing it as a dipole, I'll write simply that, let's say this is my point A. Let's say it is occupied by charge Q minus Q. And this is my B. Let's say it is occupied by Q. Only then your dipole moment will be in this direction, isn't it? And let's say this distance is dr, or let's say dx is this direction. Okay. Now because of this A, there would be A dash here, and this B, there would be B dash here. Okay. And this charge minus Q will be replaced by Q here, and this charge Q would be replaced by minus Q. So strangely, you will find that dipole moment if is in this direction for the dipole characterized by AB, and the image dipole moment also is in the same direction. So probably this may be asked in exam. Child may get confused. Probably he may think, okay, आप charge Q यहाँ पे लेते हो, minus Q लेते हो. So probably one may be tempted to say that if dipole moment P vector is in this direction, then the image dipole moment will be in the opposite direction. But this is not the case. Is that clear? This is the first observation that you should make right now. Is that clear? See, because of this minus Q, there is a Q here, and because of this Q, there is a minus Q here. And dipole moment vector always is in the direction from negative to positive. So your image dipole moment is also in the same direction as that of the original dipole moment. Is that clear?
Yes, sir. Clear.
Okay. Now let us first try to formulate the force expression. This is something that we know from standard 12th also, but I'll derive it somehow. What would be force at A? So whatever electric field is at A from the various sources, force at A would be minus Q into electric field, if you remember. And what would be force at B? The force at B will be because this particular you will have force in this direction, right? And force at B would be Q times electric field at this particular point B. So obviously, if I'm saying that my electric field at point A is E, there would be some increment in the electric field, and I'll write that increment as E plus dE. Is that clear? See, what I want to find, I want to find force on the dipole. So I'm making it I'm writing it as an easy problem. So how to write it in easiest fashion? I will, instead of using the term point dipole, I'll say that, and what would be dipole moment? So I'll write dipole moment will be equals to Q times dx here. Dipole moment क्या होता है? आप charge को किससे multiply कर देते हो? Multiply it with the distance. So what is the force at A? The force at A would be given by minus U into E. So force would be in this direction. And what would be the force at B? Force at B due to various other charges. So it would be Q times E plus dE. Is that clear? This is
yes, sir.
So net force would be equals to what? It would be equals to what? Net force would be equals to Q times dE. Is that clear? This would get cancelled. So in any case, if I want to divide it by dx, I'll write dE by dx here. And what is Q dx? Q dx is nothing, but it is equals to dipole moment P dE by dx. Is that clear? So force on the
Yes, sir.
dipole with the dipole moment P is given by P times dE by dx. And this is what I'm writing in magnitude right. This is all I'm writing in magnitude right. Okay. Okay. Now, if I want to find first, I should first find what is the electric field. So one knows that electric field due to dipole is given by P vector dot r cap divided by 4 pi epsilon naught r cap. If you remember, I mean, this was the formula. If you remember,
Yes, sir. P r cos theta.
है ना ऐसे कुछ फॉर्मूला था राइट या फिर कुछ और था फॉर्मूला एक मिनट जस्ट लेट मी हेल्प माय सेल्फ मेरे को फॉर्मूला निकाले लूंगी तो फिर दिक्कत आएगी along the axis ना along the axis देखना right sorry so electric field my mistake so electric field ये तो था potential this was your potential my mistake ठीक है this was your potential and what was your electric field your this was r square I think right नहीं यही था ना दिस वाज आर स्क्वायर है ना हम लोग क्या कहते थे कि पोटेंशियल ड्यू टू मोनोपोल इज इनवर्सली प्रोपोर्शनल टू आर
R square.
and this is r
Yes,
square
sir.
ठीक है and what would be electric field as a function of r comma theta if I remember if I differentiate this term then I will get I think this is this I can write p cos theta divided by 4 pi epsilon naught r square right and what would be electric field it can be written as minus of grad of v so I can write it as uh, so it will come as 2p cos theta divided by 4 pi epsilon naught r cube r cap and then there would be some theta cap component so theta cap component क्या हो जाएगा minus minus plus so this will be p sin theta divided by 4 pi epsilon I'm not concerned about this theta cap ठीक है okay is that clear so along the axis in which I'm interested right now along the axis only I'm interested right now so along the axis along the x-axis my electric field as a function of x can be written as 2p cos theta cos 0 is 1 2p upon 4 pi epsilon naught x cube is that clear
Yes, sir. Theta component will be r cube only, sir.
अच्छा आर क्यूब होगा क्या
क्योंकि
हाँ
जब
हाँ
मैं
एक वन
r
अपॉन आ रहा था राइट एक वन अपॉन आ रहा था सॉरी सर है ना एक वन अपॉन आ रहा था आई एम सॉरी है ना वही कह रहा हूँ ना माइनस वन अपॉन आर डेल वी अपॉन डेल थीटा
हाँ जी, हाँ जी.
okay
Yes.
okay sorry so electric field as a function of x along the x-axis would be 2p upon 4 pi epsilon naught x cube right and what would be the force then force would then be equals to p times dE by dx so what is dE by dx so dE by dx would be I think 6p upon 4 pi epsilon naught x cube power okay in magnitude I'm writing all these things I'm writing in magnitude because this will be negative so negative implies that as I go along increasing x my electric field is decreasing okay because if I don't like if I differentiate I'll get negative now so I'm writing magnitude of force right okay so what would be the magnitude of force the magnitude of force would be this would be magnitude of force would be 6 p square divided by 4 pi epsilon naught x ki power 4 now your dipole was placed at a distance x equal to l right and obviously this dipole is going to feel the force due to this dipole, the image dipole, which is placed at a distance in totality 2L. So your answer would be force on the dipole would be equals to what? It will be equals to 6p square divided by 4 pi epsilon naught 2L की whole power 4. Is that clear? देखो हमें क्या निकालना था फोर्स ऑन द डायपोल निकालना था फोर्स किसके कारण आएगा बिकॉज ऑफ दिस डायपोल और ये डायपोल इज प्लेस्ड एट अ डिस्टेंस 2L. Is that clear?
Yes.
So it will be 6p square, and this is I think 16, 16, 4, 30, 64 pi epsilon naught L cube. So force on the dipole is given by 3p square divided by 32 pi epsilon naught L cube. Is that clear?
Yes, sir.
Okay. So I hope this is enough for this lecture, and then we'll meet at the other end. Okay.
ओके सर।